Here we go again. Okay, differentiation of trigonometrical functions. Quite a few of these results we're going to quote, but then you'll see some of the other results. You'll have to use some of the rules that you already learned. Chain rule, quotient rule, and so on. We're going to start with y is equal to sine x. That is quotable. The only other way you can know what the result is if you learned what differentiation from first principles, what that is, and that's Cape level, or at least they put it in the Cape level syllabus. So we're not going to worry about that. We'll just quote the result. If y is equal to sine x, you're allowed to quote that dy dx is equal to cos x. If y is equal to cos x, you're allowed to quote that dy dx is equal to minus sine x. When you differentiate the sine function, you get cos. When you differentiate the cos function, you get minus sine. Don't mix them up. Okay. Here's the next one. Y is equal to cos squared x. How about that one? How do we differentiate cos squared? Well, one thing you may want to do is to rewrite the cos squared x to look like this. Y is equal to cos x all squared. That's what cos squared x means. The cosine function squared. But if you visualize it this way, clearly you can see the chain rule coming into play, where the function is written as a function of x to the power, right? That's written as f of x to the n. And you remember how you applied the chain rule when y was f of x to the n. When y was f of x raised to the n. You remember the rule? dy dx was n times f of x to the power n minus 1 times f prime of x. You differentiate what's inside the bracket. So let's see if we can apply it there. If y is equal to cos x all squared, dy dx will be, drop the power 2, write back the function inside the brackets, cos x to the power 2 minus 1, or 1. And then you differentiate what's inside the brackets to get minus sine x. Okay, let's tidy that up a bit. Dy dx is equal to, I'll pull the minus all the way to the front, minus 2 sine x cos x. I haven't done any trigonometry with you yet, but if you, whether you know now or not, you're going to certainly learn later that this portion that I've bracketed off there, there's something called a double angle identity for it. So at this point, if you're not, you can leave it like that. But you can definitely simplify that as dy dx is equal to minus, and 2 sine x cos x can be written as sine 2x. If you don't fully understand how we got from there to there, don't worry about it. When you do your trigonometry, which is next week, by the way, I got a couple more videos to do on integration, and then we go into trigonometry. All right, so dy dx is equal to minus sine 2x. If you don't understand how I got from minus 2 sine x cos x to that, don't worry about it. You'll know soon enough. All right, so that's how you differentiate cos squared x. Okay, what else? Let me delineate these things, man. Ice cream man. Not today, Mr. Ice Cream Man. Not today, my brother. I'm busy making videos. Y equal tan x. Now I can quote that, but at this level, I don't want to, because that involves a trig ratio that's not part of your syllabus. So here's what we're gonna do. If you know a little bit of your trigonometry, you should know you can write tan x as sine x upon cos x. We're going to prove that when we do trigonometry. And if you look at that, that's a quotient. So therefore the quotient rule can be applied. I'll call the numerator u. You remember? U is equal to sine x. And the denominator v. V is equal to cos x. Du dx, well, when you differentiate the sine function, remember you get the cos function. And dv dx, when you differentiate the cos function, you get minus sine function. Quotient rule says that to get my dy dx, I have to take v times du dx minus u times dv dx all upon v squared. Dy dx is equal to v was my denominator, so that's cos x, times the differential of the numerator, which is the du dx, that was cos x as well, minus u is sine x, times the differential of the denominator dv dx, that's a minus sine x, all over v squared, all over cos squared x. Dy dx is equal to cos x by cos x is cos squared x, minus sine x by minus sine x, minus and minus gives me a plus sine squared x, all upon cos squared x. Now again, you would have had to know a little bit of trigonometry here, but maybe you know, maybe you don't. I don't know if you would have known this from your CSEC days. There's a trig identity that says cos squared x plus sine squared x will always give you 1, irrespective of the value of x. Cos squared x plus sine squared x is 1. Therefore, my numerator is 1, and therefore dy dx, when I differentiate tan x, is equal to 1 upon cos squared x. And I'll leave it like that for this maths course. There are other ways you can re-express that, but for you guys, that's all you need. Next, how about if y is equal to the sine of a function of x, not just sine x? Sine of a function of x. Well, the rule to differentiate this would be dy dx is equal to f prime of x times the cos of f of x. F prime of x means you only differentiate this guy here and put it in front. So let's try an example. Suppose y was equal to the sine of 4x plus pi upon 3. Pi is a constant, so pi upon 3 would be a constant. According to my rule, dy dx has to be equal to, I have to take the f of x, which is, this is written in the form sine of f of x. I have to take the f of x part, which is the 4x plus pi upon 3, and differentiate that. By now, you should be very familiar with differentiating that. That's a standard polynomial in there. 4x plus pi upon 3. You differentiate the 4x, you get 4. And of course, you differentiate the pi upon 3, you get 0. So if the f of x part is 4x plus pi upon 3, the f prime of x part is just 4. And then just times the cos of the same f of x. 4x plus pi upon 3. Very simple. Let's try a couple more examples right in there. Suppose I have y is equal to, I'll put a constant in front. Let's say 5 times the sine of pi upon 6 minus 2x. Okay, well, let's see. You multiply by 5. So once you multiply a function by a constant, you don't do anything with that constant. Dy dx is equal to, you write back the 5, and then you differentiate the sine function. Sine of pi upon 6 minus 2x. The f of x part in there is the pi upon 6 minus 2x. If you differentiate pi upon 6 minus 2x, you just get minus 2. Remember, pi upon 6 is a constant. So you just get the minus 2. And then times the cos of pi upon 6 minus 2x. If you tidy all that up, you get dy dx is equal to minus 10 times the cos of pi upon 6 minus 2x. There. Okay, so just a couple of examples. Let me space them out a bit. There. Okay. Let's try one with the cos of f of x. What's the rule for differentiating cos of a function of x? It'd be nice if I could make some space in the middle there, man. Oh boy. I can't do anything. It's stuck. For real? I'm gonna have to end this video here. Jesus. What did I do? I don't know what happened there, but hopefully I still have the same video. Yes. I'm somewhere around here. There we go. Yes, if y is equal to cos of a function of x, then dy dx is equal to minus f prime of x times the sine of f of x. Let's see how that works. If y is equal to, let's say, 4 times the cos of just 3x. Well, what's the f of x in this case? The f of x is at 3x. According to the result, dy dx will be minus f prime. Well, f of x is 3x. F prime of x is just a 3. Minus f prime of x would be minus 3. Of course, I have to write back my 4 times the minus 3 times the sine of 3x. dy dx minus 12 sine of 3x. Simple. How about one with both sine and cos at the same time? This is interesting. Y is equal to uh, 4 sine of 5x minus 5 times the cos squared of x. Now, let's remember, differentiation distributes over addition and subtraction. So I'm allowed to differentiate each part separately. dy dx, but before I do dy dx, I'm going to rewrite the function as y is equal to 4 sine of 5x minus 5 times cos x all squared. This part requires differentiating sine of f of x, and the other part requires me using the chain rule. So this is a nice one. dy dx here will be 4 times the f of x is 5x. When I differentiate sine of f of x, I get f prime of x times cos of f of x. The f prime is just the 5, and then just cos of 5x minus 5 times. The chain rule here would require drop the 2, write back the function, subtract 1 from the power, and then times differentiate what's inside the brackets. I'll end up with minus sine x. dy dx is equal to 20 cos 5x minus a minus gives me a plus 5 2 is 10. You know, let me write it as, here's how I'm gonna write it. All right, instead of writing it as plus 10, I'll write it as plus 5 times 2 times sine x times cos x. Right, minus a plus, sine x cos x 2. And you remember before we talked about this part here being what's called a double angle identity. dy dx will end up being 20 cos 5x plus 5 sine 2x. Voila. That's your dy dx in this case. Other examples. Combinations. Notice I have combinations of functions. Let's run them one at a time. This one is made up of a polynomial and a trig function. Not a problem. Differentiation distributes over addition and subtraction. So you could treat each one separately. dy dx, differentiating the polynomial, everybody's an expert at that by now. That's just the 2x. And differentiate sine 2x, that's in the form sine of f of x. The result will be f prime of x. Differentiate the 2x to get 2 times the cos of the same 2x. If you choose to, you can factor out the 2, and you're left with x plus cos 2x. There. That's dy dx. Can't get any easier than that, man. Okay, let's check the next one. This is, instead of x squared plus sine 2x, is x squared times sine 2x. How do you think you'll approach that? X squared times sine 2x. Well, that's actually the product rule because it's a product of two functions of x. So product rule required here. Notice one part of the product is a polynomial. The second part of the product is a trig function. So u is equal to x squared and v is equal to sine 2x. du dx, that's 2x, no problem. dv dx is equal to 2 cos 2x. Remember that's in the form sine, v is sine of f of x. So dv dx would be f prime of x times cos of f of x. And then we apply the product rule that says to get my dy dx overall, I need v times du dx plus u times dv dx. All right, let's see how we're going to work that. dy dx is equal to v, which is the sine 2x, times du dx, which is the 2x, plus u x squared times dv dx, 2 cos 2x. dy dx is equal to Pull the 2x in front of this one. 2x sine 2x plus 2x squared cos 2x. You can leave it like that. If you choose to factor out what's common, 2x is common. 2x into sine 2x plus, if 2x comes out from 2x squared, only x is left over. X cos 2x. So product rule there. Notice how I'm starting to mix all the rules up. You're supposed to be able to see that at a flash, right? The one before, this one here, yes, it was a combination of a polynomial and a trig function, but they were added together. So differentiation distributed over addition, not a problem. We applied it in that form. This was the same two parts, x squared and the sine 2x, except in this case we were multiplying the two. So it was the product of two trig functions, one being a polynomial, one being a trig function. And therefore the product rule was required. Here's another one. Here's this one. Y is equal to sine 2x upon x squared. Well, the numerator is a function of x. It's a trig function, but it's a function of x nonetheless. The denominator is also a function of x. It's a polynomial function, but a function of x nonetheless. So you would never guess what rule is required here. I know you know. The quotient rule is clearly required here. So remember, the numerator is always u in my quotient rule. U is equal to sine 2x. The denominator is always v. V is equal to x squared. Du dx is equal to, this is in the form sine f of x, f prime of x, which is 2, times cos of f of x. dv dx is equal to 2x. That's a regular differentiation of a polynomial. dy dx is equal to v times du dx minus u times dv dx, all upon v squared. Let's plug in. dy dx is equal to v x squared times du dx, which is 2 cos 2x minus u sine 2x times dv dx, which is 2x, all upon v squared, which is x squared all squared. dy dx is equal to 2x squared cos 2x minus 2x times sine 2x, all upon x to the power 4. A little bit of indices there. And what else can I do? I can factor out a 2x. dy dx will be equal to 2x comes out. What's left inside in my numerator? X cos 2x minus sine 2x, all upon x to the 4th. This x will go with one of these x's, and I'm left with x cubed on the bottom. So finally, I'll write my end result for dy dx as 2 into x cos 2x minus sine 2x, all upon x cubed. How you like them apples? And that's the last problem I'll have here, and that's the end of this video. What I've done actually is I've set up an entire worksheet. I'll show you here, but it'll be at the end of the next video. This entire worksheet right here. You can take a look at it. This is from your standard text that we are using. All of these, end of differentiation and application. This will be the end of everything associated with differentiation. So when I'm finished with the next video, I'm showing it to you now, this will cover everything on differentiation, including the last 3 videos. Notice I didn't give you any homework problems on the previous worksheet that dealt with the chain rule, product rule, quotient rule. I'm not going to give you any homework problems on the video I just finished, which is differentiating trig functions and so on. However, this last I have one more video to do for the differentiation applications involving rates of change, at the end of which you're going to get one big worksheet. Here it is. That's a lot of problems. In fact, yes, I can simply, yeah, there it is. This entire worksheet has everything to do with the differentiation you've done. All the differentiation, everything, all the applications. So, one more video on differentiation and then that's it. All right, I'm out.